In the last few videos, we worked to define these linear algebraic K-forms, which remember is the kth wedge power of the dual to our vector space V, which is just some r to the n. And so in layman's terms, this means you plug in k different vector inputs to some function and spits out a real number. And remember that this was supposed to represent some sort of k-dimensional volume on our vector space, except not quite, because you can add up different things by linearity. And so in this video and the next couple of videos, we'll be discussing differential K-forms, which is the main tool that we need to even define the Rham Cohomology. And once we have these defined, basically we'll be able to discuss the Rham Cohomology in full generality. In this video, I'll be restricting myself to subsets of Rn, but in later videos, I'll discuss sort of the more general way of talking about differential K-forms in terms of manifolds, and I'll introduce all the terminology there. So some things in this video may make more sense from an abstract point of view after watching the later ones. There isn't a particularly good way to linear order these topics, but you might enjoy coming back to this one after understanding some more general manifold theory. But for the purposes of this video and the next few videos, whenever I write M, this denotes some subset of Rn. So either like some subset of R2 or R3 with some missing patches, or maybe you have something like a sphere which is embedded in R3. And when I talk about the tangent space at a point, what I mean is that we have some point P. And what you should think about when I talk about the tangent space is a vector space that is attached to the point P, called TPM, for the tangent space to M at the point P. And this vector space will be just spanned by basically all vectors which are tangent to the point P. So if your space M is just R to the n, then this is some n-dimensional vector space. But for example, if we're talking about the sphere, then the tangent space is going to be, at this point P, is the set of vectors which are tangent to the sphere at that point. And if we have some sort of a curve, then the tangent space at this point is going to be a one-dimensional vector space, which is the tangent line to that point. And so later on, we'll define manifolds more generally and the tangent space more generally. But given this notion of a tangent space on a manifold, it's actually not too difficult to define differential K-forms now that we have all the machinery that we use to define K-forms. So differential K-form, what it is it's a linear algebraic K-form attached to every point in space. And so the way that that works is it takes in k different vectors from your tangent space at your point P. For every point P in your manifold, you're going to have a different K-form. And the K-form is supposed to vary continuously in some sense. And so I won't talk about continuity in the precise sense because that's a bit annoying. And I won't give specific definition for differential K-forms other than what I just vaguely said, that it's a linear algebraic K-form attached at every point where the input vectors are from the tangent space at that point. And instead, I'm going to focus primarily on giving a bunch of examples. So hopefully you get a feel of what these things are doing. So let's first, as always, restrict ourselves to R2. And so in this case, at every point P, our tangent space is spanned by two vectors. I'll call them E1P and E2P. And E1P is pointing in the x direction, and you can think of it as having a length of 1, and E2P is pointing in the y direction and having a length of 2. So if we have another point Q, then this can be spanned by two vectors again, E2P, and this can be, sorry, E1P, E1Q, and this is E2Q. And so this vector space is TPM, and this vector space is TQM. So the first differential form that we can write down, differential one form, is this one form dx. And so this is a differential one form, which means I should take in one vector input from every tangent space and then spit out a real number. And so what this is going to do is at the point P, it's going to take in the vector A, E1 plus B, E2, or E1P and E2P, and then spit out the number A. So in other words, if at the point P, you are considering the input to be this vector V, then the output is just going to be the component in the x direction. So for example, what we can do is if we have a differential form like dx, then we can evaluate it on a vector field, because a vector field is a vector at every point. So what this does is if you have something that looks like that, like that, like that, like that, some sort of a vector field along your space, then let's call this vector field V. We can evaluate dx at V. And what is this going to be? Well, this is going to be a function. So this is going to live inside C infinity. And let's call this function f. And the way that this works is f of p is going to be dx at v of p. And so I guess I should call it dx of p. So dx at p is going to be some one form at the tangent space of p, and vp is going to be the vector of this vector field at that point. So for example, over here, maybe this is 2 units right, 1 unit up. So if this point is p1, then f of p1 is equal to 2, if this is 2e1. This one, it doesn't go horizontally at all, so if we call this point p2, then f of p2 is going to be equal to 0. And similarly, you have some value of your function here, which corresponds to how horizontal this vector is. And then the output of dx on this one is going to be 0 because it doesn't go horizontally at all. And so hopefully you now get the sense that this dx is saying that at every point, take your vector at that point and then measure the horizontal component of it. Okay. So that's the first example. The second example, which is a bit more interesting, is going to also be a subset of R2, but we're going to consider the form omega is equal to x squared dy. And so omega is going to be the common notation I'm going to use for differential k-forms. And this is, again, a differential one form on R2. And so the way this is defined is dyp, which is the one form at the point P, is going to take in the input of some vector at your point P, and it's going to measure the vertical component. So if this vector is the vector 2, 2, so I'll use angle brackets to denote vectors and round brackets to denote points. So if this is the vector 2, 2 at the point P, then dy on this vector is going to be equal to 2 because it points 2 in the vertical direction. And so similarly, what you can do is you can construct some vector field, and then you can evaluate your one form at every point. And so this is what dy does. It excludes out the vertical component, but what do I mean by x squared dy? Let's compute this at a few points. So let's say that we take the point 2, 0, 2, 3, and 0, 1. Okay, so let's say that P1 is equal to 0, 1. And let's see what omega at P1 is going to be equal to. So what does this do? It takes as input some vector in the tangent space of P1. So maybe something like that, or something like that, or something like that. Takes in some vector and then gives you some output. And so what do I mean by x squared dy? It means that at the point that you're considering, so at P1, plug in the coordinates of x and y at that point for these functions. So in this case, it's x squared. So we're going to plug in 0 for x because the point is 0, 1. And so this gives us 0 dy. And so this is going to just be the 0, 1 form. And so this says that for any of these tangent vectors at P1, this is just going to output 0. Now let's consider this point P2. And here again, our input is any vector at P2, and it's going to output a real number. So what is omega of P2? Well, now we're going to plug in 2 for x because we're at the point 2, 3, and this is going to give us 4 dy. And so, for example, if this vector is negative 1, 2, then it has 2 in the vertical component. So this is going to give us that wp2 on this vector v is going to give us 4 times 2, which is 8. And also, if we denote this point by p3, then notice because the x-coordinate is the same, it's 2. So w at p3 is also going to be equal to 4 dy. So what I'm doing here is I'm saying that your one form is expressed as some function times some dy. Or it could also be, we can also add on something like y dx. And so how you would evaluate this one form is at some point, a comma b, you would plug in a for the value of x, you would plug in b for the value of y, and then you would keep dy and dx the same, where dy and dx measure the horizontal and vertical components of the vectors at this point. So yeah, that's our first couple examples of forms. Okay, so now that we've seen an example of a one form, you may be asking, how can you construct one forms? So one way to do it is the way that I just said is, so for example, you can just take omega is equal to any function f of x, y, dx plus g of x, y, dy. And f and g are just two arbitrary functions of your inputs. And then, so at the point p equal to ab, what is this saying? This says that wp is equal to f of ab dx plus g of ab dy. So this is going to say wp at some vector v, which is in the tangent space at the point p of m. It's going to take the horizontal component of your vector, and then dx of v is going to be that horizontal component, and multiply that by f of a comma b, where a comma b are the points of p, coordinates of p. And then it's going to take the vertical component, and then that's going to be dy evaluated on v, and then multiply that by g, and then take the sum of those two values, and then give you a real number. So that's how you evaluate this one form at the point p. However, a natural way that you can get these one forms is by starting with the function f, which is some c infinity function. And what you can consider is the one form df. And so what is this defined as? This is defined as the following. So df, valued at the vector v, or df of p, I guess, at the value at the vector v, says how much f changes at the point p in the direction v. So for now, you can explicitly write this as f of p plus v is equal to f of p plus d f p v. Sorry, I should write this as f plus tv. So t is just some real number times t plus O of t. So O of t just means smaller terms. If you haven't seen this notation before, don't worry about this bit. It just says that to first order approximation, this is what your function looks like. And so this is basically saying what is the derivative of our function at p. And so what this means is that df at p is equal to partial f partial x evaluated at p dx plus partial f partial y evaluated at p dy. So if that seemed a bit too abstract for you, let's just go through an explicit example. Let's say that we have the function r is equal to the square root of x squared plus y squared. So this function r obviously measures the distance from the origin in R2. So also this expression is only for R2. You'll have to add a dz term for 3 dimensions and so on and so forth. So in R2, the picture is we have this, and then r is just measuring the distance from the origin. So let's compute what dr is. Dr is going to be x over square root x squared plus y squared dx plus y over square root x squared plus y squared dy. And so that just follows from this formula. And let's see what this looks like at some specified vectors. So let's say that we take the point p is equal to 3, 4. And let's say that we take two vectors and evaluate dr on them. So let's say that we take the vector v1 is equal to -4, 3, and v2 is equal to 1, 1. So if we write out what dr at p is, this is going to be equal to, well, the exponent is 3, and then squared x plus y squared is square root 9 plus 16, which is 25, which is 5. So then you get 3/5 dx plus the y coordinate is 4, and so you get 4/5 dy. And so what is it saying? Let's evaluate on v1 and see what it says. drp of v1 is equal to 3/5 times dx v1 plus 4/5 times dy v1. And so this is going to be equal to 3/5 times -4 plus 4/5 times 3, which is equal to 0. So this is saying is that dr at the point P, evaluated on the vector v1 is equal to 0. So what that means is, by its interpretation, this should mean that our function r does not change as we move in the direction v1. This makes sense because if you think about it, we can make the unit circle, or not the unit circle, but the circle through the origin that passes through the point P. This is a bad drawing, but just imagine this is a circle. And v1 will be the tangent vector to that circle at that point. And because r takes the same value along the circle, if you move along the direction v1, then your function r does not change because you're staying at the same distance from the origin. And so that's what this dr is measuring. It's saying that your function does not change. Okay, let's evaluate drp of v2. This is equal to 3/5 times 2. 3/5 times 1 plus 4/5 times 1, which is just equal to 8 over, or no, I can't do math, 7 over 5. Okay, so what's the interpretation of this? Well, you may realize by now that if we take the vector 3 over 5, 4 over 5, well, that kind of looks like the normal vector to the circle at the point 3, 4. And indeed it is. And so what this is doing is it's taking basically the inner product of the normal vector with the vector v2. And so it's saying how much of the v2 direction points in the points away from the origin. And that makes sense because if you think about it, at the point P, we can choose two basis vectors, e1 and e2, which are the horizontal and vertical directions, but we can also choose two vectors which looks like this, which are the tangential directions to the circle at the point P and the normal direction to the circle at the point P. And our function r does not change if we move along in the tangential direction, but it does change if we move along in the radial direction. And moreover, it changes in such a way so that if you have some arbitrary vector v, then the amount that changes if you move a little bit in the direction v is determined by taking the inner product of your vector v with the direction perpendicular to the circle. And so you can check that that intuitive understanding agrees with this because the coefficients here turn out to be the coefficients of the unit vector in the direction normal to the circle, as we expect. And so you may be saying to yourself that this looks a lot like the gradient, and indeed it is the gradient, except with a small exception. So how does the gradient work? Well, if we take the gradient of our function f, and we want to determine, sometimes it's written as like dv of f, so like how much does f change in the direction of v? This is equal to the inner product of the gradient of f with v. And so now I'm using angle brackets to denote inner product instead of coordinates of a vector, but there aren't enough notations to be able to distinguish everything. So this is saying that if you take the gradient of a function and take the inner product with the vector v, then it tells you how much does the function change in that direction. However, now I'm saying that this is equal to df evaluated on the vector v. And essentially these two are the same notions. But it turns out that df is the more natural thing to define. If you know a little something about metrics, then you'll know that this inner product notation depends on what metric you choose. But this df definition does not depend on the metric. Maybe as we'll see a little bit in the later videos. But it turns out that this is the more fundamental notion to define, while this is actually defined through having this, what we'll later see is the exterior derivative in later videos. So the main point that I want to say here for now is that it turns out that there are many different notions of derivatives as you move into higher dimensions. To sort of generalize the notion of derivative that you learn in the first calculus course. There is this notion that I'm building up to, which is the exterior derivative. There's also something called the covariant derivative. There's also something called the Lie derivative. And these act on different objects, either differential K forms, maybe tensors, or other things. But the one thing they have in common is basically that if you evaluate them on a function, then they will all give you the same object, which tells you if you move a little bit in the direction v, then how much does the function change? And as you generalize these from functions into other things, then you get wackier and wackier objects. And so the exterior derivative is one of the sort of generalizations of this. Another couple points that I wanted to make about this. The first is I'll leave it as an exercise to verify that dx is equal to dx. So this seems like a really stupid statement, but what I mean by this dx is the dx that I had a bit earlier, where dx at the point P, evaluated on some vector v, gives you the horizontal component of that vector. And this dx says, okay, we can consider x as a function from R2 to the real numbers, which takes in a point AV and just spits out the number A. And so this dx is saying, if you move at the point P in some direction V, then how much does the x coordinate change? And so sort of convince yourself that how much the x coordinate changes as you move along in some direction V is just equal to the horizontal component of V. And similarly, do the same thing for dy. And another nice exercise to do is, we saw that you can sort of get one forms out of taking this df procedure. And so verify that this one form that we had earlier, x squared dy, is not of this form. In other words, there is no function so that df is equal to this. And so one hint that I have towards that is that the curl of the gradient is always equal to 0. And so this is sort of like the gradient of a function, except technically not because of this. So try and see if you can show why this is not d of any function. And another thing that I want to point out was that I said that one way to get a one form was to start with a function and then construct this df object. Another way to get a one form is by looking at this observation, which says that the gradient of v is some vector field, while df is really some one form, more precisely a differential one form. And this inner product sort of gives you a way to go back and forth between vector fields and differential one forms. And so this is what physicists do a lot of the time, what they call raising and lowering indices. But if you know a little something about metrics, even if you don't, I mean, you can still talk about these things with the standard metric on Rn. You can have an exercise to show that if you have some vector field v, so some vector field on Rn, then you can construct some one form, which I guess I'll call omega sub v. And so how this works is, if you have some other point P, and you evaluate it at W at the point P, then this is a lot of symbols, but let's say that we have some vector field V, and we take some point P, and we have some other vector W at this point. Then the way that we're going to define this one form at the point P on the vector W is to say that if this is V of P, the vector at P defined by this tangent vector field, then this is just going to be the inner product of V comma W. So verify that if you have some vector field V, then this defines one form as follows. And the last thing maybe that would be good to mention here is that sort of the procedure that I've been saying is that a one form is something that takes in a tangent vector at every point and then spits out a real number. And so another way to say that is that if you have any vector field, then it spits out a function. And we've seen that before. So maybe this would be a good place to say that, is that one form is a function which takes in a vector field and then spits out a z infinity function. And so when we start talking things a bit more abstractly, we'll see that these vector fields correspond to something called the tangent bundle over manifold n, and these one forms correspond to what is called the cotangent bundle. And so that's denoted by T star m, and this T star is supposed to be like the same sort of star as the linear algebraic dual that we went over earlier. So the last thing that I want to mention is why do we actually care about these differential K-forms? Well, these differential K-forms are things that you can integrate. And so right now I'll sort of give the first demonstration of how we can integrate differential K-forms, or what the interpretation of the integral is. So let's say that we have some differential one form on R2 written as f is equal to fx dx plus fy dy, where fx and fy our functions. Then let's say that we have some path, gamma of t is equal to gamma 1 of t, gamma 2 of t. So this is some parameterized path in R2. So it looks something like this. And we have a one form f. So we can write what the integral over gamma of f is going to be. And what is this going to do? Well, to every point of gamma, you can take the tangent vector, which will look like the vector gamma 1 prime t, gamma 2 prime t. And so what you can do then is evaluate this one form on this tangent vector. And so what that'll give you is the integral of f of fx times gamma 1 prime t plus fy times gamma 2 prime t. And so this fx and fy is not supposed to mean that I'm taking the derivative with respect to something. These fx and fy's are just arbitrary functions in R2. And what you're integrating over is that, let's say that t varies from 0 to 1, then you're going to integrate this from 0 to 1 dt. And so the way to interpret this is that you're taking the tangent vector that's caused by this curve, and you're feeding that into this one form f, and then you're integrating that. And so the reason that I chose the letter f was to be a bit suggestive in that when you're doing forces in physics, technically the force field is not actually a vector field. It should be better interpreted as one form. And the same thing holds for the electric field, for example. And so what's really going on with those is you really like integrate them to get energy, or you can write the force as the gradient of energy. But as we saw, it should really be written as the force is equal to sort of this exterior derivative of energy, which we'll define better later. And the energy is equal to the integral over some curve of this one form f. And so that's basically how you can do one-dimensional integrals using one forms, and the same thing holds in 3 dimensions. I encourage you to try and figure out how that looks. Another interpretation that you can have on this is that you have these dx and dy terms. And so what you can do is you can also say, okay, we can take our path, which sort of looks like R1, and this maps into R2 through gamma. And so what we can say is that now on this function gamma, gamma 1 of t is basically some function x of t, right? So it's saying as t varies, how much does the x coordinate vary? And then gamma 2 of t is similarly some function y of t. And so then you can write is that dx can be considered as a one form up here, which says as you vary t, how much does the x coordinate vary? And if you sort of use the same formula that we had before, then this will come out to be gamma 1 prime of t dt as a one form on the line instead of as a one form on the plane. And so these two different modes of integration is sort of two dual perspectives on things. We'll discuss this terminology later, but this is basically saying you're taking the push forward of some tangent vector from the curve into your plane, and then evaluating that tangent vector on this two form on the plane. And the second interpretation is saying you have a one form on the plane, and you're pulling that back to one form on the line, and then you're integrating that one form on the line. And so we'll discuss manifolds and integrals and tangent spaces later on, and hopefully that'll make more sense then.